Hello students, welcome to Saurabh Sir classes. Today's topic, design of experiments. Note, the percentage SE to which the mean effect of a treatment replicated R times is 100 sigma by root over n minus 1 root x equal to 100 sigma by x bar one by root n equal to c dot v by root n, where Cv is the coefficient of variation. If x1 bar and x2 bar are the mean effects of two treatments replicated R1 and R2 times respectively, then variance x1 bar minus x2 bar equals to variance x1 bar plus variance x2 bar. Convergence term vanishes since x1 bar and x2 bar are independent. Then variance x1 bar minus x2 bar equals to sigma square 1 by R1 plus 1 by R2, where sigma square as usual is estimated from error variance. So SE x1 bar minus x2 bar equals to sigma 1 by R1 plus 1 by R2 whole to the power half, that equals to sigma root over 2 by R if R1 equals to R2 equal to R, say. An approximate idea of the minimum number of replication required to detect the given difference between two treatments at certain level of significance is obtained by applying normal test to the statistics. Now small t equal to x1 bar minus x2 bar by SE x1 bar minus x2 bar equals to x1 bar x2 bar sigma root over 2 by R for a large number of degrees of freedom. However, for small degrees of freedom, small t is not normally distributed but follows students' t distribution. Here t is small t. In that case, the approximate minimum number of replication required to detect a specified difference called small d between the treatments at alpha percentage level of significance is given by the formula where small r equals to 2 small tv alpha by 2 se square by small d square, where AC square is the error variance per unit and TV alpha is the right tail critical value of small t and alpha level of the significance, and small v equal to error degree of freedom. I repeat, where AC square is the error variance per unit and TV alpha is the right tail critical value of small t at alpha level of significance, and small v equal to error degree of freedom, so that capital P t greater than TV alpha equals to alpha. From appendix, we observe that the critical significant value of t decreases as v the degrees of freedom increases. For example, we have t1 0.025 equals to 12.71 and t6 equals to 0.025 equals to 2.45. Like that, t15 0.025 equals to 2.13 and t25 0.025 that equals to 2.06. Therefore t infinity equal 0.025 equals to 1.96. Thus, the increase in the number of replication will result in increased accuracy, since in that case even small difference will be detected. Okay, here is a problem. Calculate the minimum number of replication so that an observed difference of 10% of mean will be taken as significant at 5% level, the CV of the plot values being 12%. Now, where is the solution? If small r is the required number of replications and mu be the common mean, then we are given C dot V equals to 12 equals to 100 dot sigma by mu, that imply sigma equals to 12 mu by 100, 0.12 mu, and x1 bar minus x2 bar equals to 10% of mu equals to 0.10 mu. Therefore, small t equals to x1 bar minus x2 bar 2 by r equals to 0.10 mu by r. For be significant at 5% level of significance, we should have mod t 1 point greater than 1.96, that imply 10 by 12 root over r by 2 greater than 1.96, that imply r greater than 2, 1.96 into 1.2 whole square, that equals to 11.1. Hence, the required minimum number of replication is 12. The next integer greater than 11.1. So, here is the solution. Now, we are knowing about size of the plot. Now, what is the size of the plot? The sorry, the size of the plot depends on a number of factors such as the total experimental area available, the number of treatments, the number of replication of each treatment, the crop, and so on. If the total experiment area remains fixed, then an increase in the size of the plot will be result in decrease in the number of plots and consequently result in an increase in the size of blocks and decrease in the number of blocks. While deciding about the number of plots, it should also be kept in mind that an increase in the number of plot increase by the non-experimental area or so-called GERD area, by which we mean that the strips of land are left out between consecutive plots and also between consecutive blocks in order to reduce the flow of experimental material from one plot to another. The second one is what is shape of blocks and plots. The shape and size of the blocks will usually depend upon the shape and size of the plots. In order to control the experimental error, it is desirable to divide whole experimental area into different subgroups or blocks, such that within each block there is an much homogeneity as possible, but between blocks there is maximum variation.